Good afternoon and welcome to today's webcast. Our topic, modeling, measurement, and verification of PCI Express 4.0, sponsored by Keysight Technologies, formerly Agilent's Electronics Measurement Group, and synopsis. I'm Bill Wong, editor with Electronic Design. Let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner of the slide window. We welcome your questions during today's event. Just type in your question into the question window on the side of your screen and hit the submit button. We'll answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. Please also be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now, let me introduce today's speakers. Pegah Alavi is a Senior Applications Engineer at Keysight Technologies, where she focuses on signal integrity and high-speed digital systems. Prior to joining Keysight, Peggy has worked on behavioral and macro modeling of analog and mixed signal circuits and components in her previous jobs. Jim Flynn, an analog and mixed signal circuits design engineer at Synopsys, has been responsible for designing and developing high-speed SerDes circuits since 2004. Jim received his bachelor's from the University of Central Florida and a master's from Florida Institute of Technology. Now let me turn things over to our presenters. Peggy, the floor is yours.
Thank you, Bill. Hello, everyone. This is Peggy Alavi, and Jim and I will be your guides, tour guides through the presentation for today. I wanted to thank you for being with us and joining us for this webinar. As we all know, communication has vastly changed in the past decade or so. We all expect to be able to check our email on the go, get live traffic updates, check in at the airport before we even get there, watch videos on our mobile devices or on the web, and video chat at any time, in any place, and with anyone. All of these are possible with the great advances in technology, which have been made possible by engineers. Let's imagine for a minute a world without engineers and see how communication and networking would be made possible. I believe the contrast in what exists today and what it would have been without engineers and without the great technology advances is a great motivation for us to talk about PCIe 4, the methods of modeling, simulation, measurement, and validation of systems with PCIe 4 transceivers. To do this, we will first take a quick look at an overview of the PCIe standard and how it has evolved over the past few years. After that, we will talk about why IBIS-AMI models are great for modeling PCIe transceivers. Next, we will do a brief overview of IBIS-AMI models. IBIS-AMI models represent the equalization performed in the transceivers. So we will first we'll take a look at why there's actually a need for these equalizers, and then briefly discuss a few common equalizer blocks. Once all of these are achieved, we will go over the steps involved in the creation of an IBIS-AMI model. After the successful creation of the IBIS-AMI model, the next step is to simulate this model and validate it. We will share our simulation results and then compare our simulation results to measurement results. With this result sharing, we will do a quick recap of what has been discussed, and we will conclude our presentation and be open to your questions. I will hand it over to Jim to present the next slide. So let me quickly go over this slide. What you're looking at is the PCIe and the 4 generations of PCIe that we've had. PCIe 4 is being worked on, and the spec will be finalized next year.
Hello, I'm sorry.
Go ahead, Jim.
I apologize. My phone, hang on. I apologize. Go ahead, Peggy. You can complete the slide. I'm sorry.
So what we can see is the data rate that has changed from PCIe Generation 1 to PCIe Gen 4, which is being worked on right now. In the very first gen, we had about 2.5 gigatransfers per second. And just to look at the contrast, that has been upped to 16 gigatransfers per second in Gen 4. You could also look at the devices and the families of devices that have been supported or can be supported in various PCI generations, PCI Express generations. And you can see that Gen 4 highly focuses on enterprise server networking, which is very high speed and also very high fidelity. Go ahead, Jim.
Thank you, Peggy. Now, what's important to note is that there's some early adaptation of PCI Express Gen 4 in the enterprise servers, networking, and storage electronics devices. And with the advent of those high data volume systems in the enterprise, it's necessary to have a quick and accurate system-level simulation and verification for fast time-to-market solutions. IBIS-AMI models facilitate early feasibility studies and system analysis by enabling fast time-to-simulation results. Relative to circuit and transistor-level simulations, IBIS-AMI models using channel simulations are orders of magnitude faster. Early system evaluation and hardware selection can also be completed using IBIS-AMI models and fast channel simulations. Channels can be evaluated early, and hardware decisions can be made quicker without the compromise of accuracy. At PCI Express Gen 4 rates, channel equalization needs to be incorporated and modeled algorithmically, which is where the IBIS-AMI model excels. Peggy will now discuss the IBIS-AMI model.
Thank you. So now that we have discussed and we have agreed that we're going to be using IBIS-AMI models for modeling of PCI 4 transmitters, let's actually talk about the SerDes system in general. A SerDes system is comprised of 3 main blocks. These are the transmitter, the composite channel, and the receiver. When modeling these blocks, we need to make sure it is absolutely clear what each model contains. The transmitter and the receiver, for the transmitter and the receiver, the IBIS-AMI model contains the regular analog IBIS model, which includes the IVM-VT table, and it also includes the AMI portion of the model. The AMI model includes the algorithmic model, and hence the name Algorithmic Modeling Interface, or AMI, or the DSP blocks. These blocks represent various equalizations that are used in the transmitter or receiver. In addition, the AMI model will include clock and data recovery blocks, which are included in most receivers now. We have discussed the transmitter and the receiver in the 3D system. Now let's focus on the composite channel. The composite channel includes the physical channel that the signal will be traveling through, all the vias, connectors, and traces. This composite channel also includes the analog IBIS model for both transmitter and receiver, as well as the the actual package model. Let's take a look at the total system and see where each of these elements that we have already talked about are placed. The orange block at the center of the screen is showing the composite channel. As it can be seen, this composite channel includes the analog IBIS model and the package model for both the transmitter and the receiver. In addition, it includes the entire channel, including connectors, that the signal will be traveling through. This composite channel is characterized with an impulse response. In a bit-by-bit simulation, a bit pattern is fed to the transmitter's AMI block, and then the resulting waveform from that AMI block is convolved with the channel's impulse response. This new waveform, which now contains the effects of the entire channel, goes through the receiver. At the output of the receiver, as you can see, the waveform contains the effects of all equalization blocks used, as well as all the channel degradation. If the receiver has a clock data recovery block, then the receiver will also output clock ticks. Let's take a look at this from a different perspective. If you recall, we earlier talked about the IBIS-AMI model. If you look at the two dark circles at the two sides, those two circles represent what is included in the IBIS-AMI model. The analog IBIS model, which is marked with the green circles, as well as the AMI file and the executable, and this executable can either be a .exe for Windows or a shared object for Linux, are represented with the purple block. The combination of the .ami file and the executable describe various equalization blocks in either the transmitter or the receiver. Finally, the orange blocks at the center represent the entire composite channel. Typically, the actual channel, which is the middle block, includes the connectors, vias, etc., and is brought into the simulation environment in one or more or multiple S parameters. Next slide, Jim. So let's talk about why equalization is actually needed.
Hello?
Yes, go ahead.
I'm sorry. I can start. I'm sorry. The composite channel used for this presentation has a loss of 8 gigahertz in Nyquist of about 33 dB. The PCI Gen 4 channel maximum loss is specified at about 28 dB. The extra loss present is due to additional test fixtures placed in the channel and their loss contributors. So in order to test our PHY, we needed to add some extra test features which pushed the loss beyond 28 dB. Now, from the channel composite loss plot, you can see that the higher frequency signal components can be as much as 20 times smaller than the lower frequency signal components. The effective result of this is an imbalance or unequal signal loss in a channel and results as interference at the receiver input. To receive data reliably, the signal must be balanced or equalized, and that is, that the lower frequency signal components need to be de-emphasized while the higher frequency signal components need to be boosted or emphasized. The methods used to equalize the signal are feed-forward equalization, or FFE, continuous time linear equalization, or CTLE, and decision feedback equalization, or DFE. Feed-forward equalization is employed in the transmitter, and feed-forward equalization adjusts the transmitted signal's digital voltage levels and equalizes the signal starting at the source. The transmitter has 3-tap FFE for pre-emphasis and de-emphasis of the signal before the signal travels through the channel. The transmitted voltage level is adjusted based on the current and previous voltage levels. You can see from the plot of the loss that the higher frequency signal components, the green arrows, using feed-forward equalization are emphasized, while the lower frequency signal components, or red arrows, are de-emphasized. Continuous time linear equalization is employed in the receiver. The received signal is equalized continuously over time within the targeted frequency range. The higher frequency signal components, green, are boosted relative to the lower frequency signal components, red. And the Bodhi plot down below shows the relative boosting levels and relative frequency ranges in peak boost. So effectively, the signal is filtered, actively filtered, and selectively boosted or gained or attenuated depending upon what frequency range that the signal falls into. A decision feedback equalizer, or DFE, is also applied to the output of the CTLE. The pulse response of the channel, including the FFE and CTLE, is shown before the DFE is applied. There on the left, it's a pulse response. It's representative of a pulse being sent down the channel and how the pulse is manipulated by the channel response. Now, the tail of the channel response extends in time and interferes with future pulses or bits at sequential unit intervals, or taps. Each tap represents the interfering component of the associated previous bit. For example, here, tap 1 is the previous bit's residue interfering with the present bit. This interference is called intersymbol interference, or ISI. Now, the equalization is applied by the FFE and CTLE, that's FFE from the transmitter to CTLE on the front of the receiver, and minimizes the amount of FSI present. The DFE now just subtracts the ISI from the previous bits on the incoming signal by using a feedback finite impulse response filter in summer. The slicer determines the polarity of the tap value. The pulse response plots show how the DFE cancels the ISI for the tap positions. Above the top plot, the pulse response before the DFE is applied. The pulse response on the left is the response after the first tap is subtracted, the red arrow, and after the first tap, and then the pulse response on the right is the pulse response after the second tap is subtracted. So both the first and second tap are subtracted, and you'll see that the interfering level is now reduced. Now I'm going to discuss the creation of the IBIS-AMI model after now I've discussed the algorithmic components that are inside the AMI model. The creation of the IBIS-AMI model starts during the circuit design phase, after the architectural design of the PHY is completed. The algorithmic components of the PHY are modeled on the architecture, and IBIS-AMI data is extracted from the circuit design, such as parasitic data, termination data, and load impedance. To achieve high model fidelity, the model should respond similarly to the circuit response, and circuit simulations are run, and parameters are extracted that fit the algorithmic response to the circuit response. This is the curve fitting or data collection step and consists of generating data model parameters such as poles and zeros for the CTLE, bandwidth measurements, and other non-idealities of the PHY. After the curve fitting data collection step is completed, the model is simulated and the response is verified versus the circuit response. This is the model simulation step. Now, the IBIS-AMI model is based on the executable version of the model, and once compiled, more model simulations are run using the executable model to verify that the model, again, still fits after compilation. Now, the executable IBIS-AMI model can now be used in system channel simulations and also used to correlate silicon characterization. This is an illustration of the transmitter model containing the FFE and the bandwidth non-ideality. The FFE parameters are defined by the architecture, and the bandwidth non-ideality is modeled as a low-pass S-domain filter, and the pole of the filter is derived from the circuit simulation and curve fitting steps I described earlier. The analog model parameters at the output of the transmitter are applied after the AMI model, and these parameters could include parasitics, termination, and even load impedance elements such as coils. This is an example of a fitted response to the TX-AMI model. The model simulation output data out is compared to the circuit simulation output data out reference for the same data input. And this measures the fidelity of the model simulation as well as your curve fitting steps during the model simulation step. Now, this is an illustration of the receiver model containing the CTLE, the CDR, the DFE. The CTLE curves are fitted from the circuit simulations by extracting the poles and zeros during the curve fitting step. The CDR and DFE are modeled based on the architecture, and any non-idealities are also present and measured and applied to those models, such as bandwidth or delay. The analog model parameters, again, for the RX are applied before the AMI model. And again, these parameters include parasitics, termination, and load impedance elements such as coils or T-coils. Again, this is similar, an illustration of the receiver model containing the CTLE, the CDR. Oops. This is an example of a plot for the fitted response of the RX-AMI model. The model simulation output, the AFE, CTLE, NL, in orange there, is compared to the circuit simulation output of the RX out, which is blue. So the same RX input, and again, the RX input is the H-SPICE simulations that we're trying to match the response of our model to, and again, the fidelity of this matching is a function of the curve fitting and the algorithms used to curve fit and how extensive your simulations are run. I will now turn over the discussion of IBIS-AMI model simulations to Pega.
Thank you, Jim. So we just got a great overview of how IBIS-AMI models have been generated, and this is the process that was used for generating the IBIS-AMI models that we are going to be simulating now. So let's take a look at the total system. And what we're going to actually do is, in order to simulate these IBIS-AMI models, we want to make sure that we use the S parameters for the various parts of the channel. These S parameters were gathered either from running EM simulations and collecting those results, or they were actually channels that were measured on the instrument in the lab, and those S parameter files have been collected. It's important to mention that we ran our simulations at 16 gigatransfers per second, which is the highest data rate for PCIe 4. We also did our simulations at 2 BER levels, 1 to the minus 6 and 10 to the minus 12. This is because we did our lab measurements at BER of 10 to the minus 6. However, the spec requires a BER of 10 to the minus 12. We wanted to make sure that we have simulations that can be directly correlated with measurements, and hence the BER of 10 to the minus 6 simulations. At the same time, we wanted to make sure we are able to compare the I at the two BER levels to make sure that we will pass the spec at BER of 10 to the minus 12. So again, you'll see in our simulation results that we actually have collected results for both simulations. Now, what you're seeing here is the simulation test bench which was used in ADS to simulate the IBIS-AMI models that have been created earlier. As you can see, we have a transmitter and a receiver set, as well as an S-parameter block in the center, which represents our channel. Once we descend into the hierarchy of this channel, we see that this channel, in fact, is cascading 6 S-parameter blocks to account for transmitter and receiver packages, as well as the vias and the traces that exist. So you can see this channel has the loss that was discussed earlier by Jim, and at 8 gigahertz Nyquist frequency, we have about 33 dBs of loss total at this channel. And that corresponds to 16 gigatransfers per second. So now let's take a look at some results. In the top left, we can see an I at the input of the receiver. As is expected for a closed I spec, this I is completely closed. At the right, you can see that this I is recovered by the receiver. The I at the output of the receiver, which is the right plot, is very open and can easily be sampled. The I dimensions, along with other I specs, are written in the table at the bottom left of this slide. A quick summary is that this I height is just a little bit over 100 millivolts, and it has an I width of about 28 picoseconds. This particular simulation was ran with a BER of 10 to the minus 12 and with a PRBS pattern of 31. We repeated the same simulation with a PRBS 11 pattern. The reason we did this was because our lab measurements were done with PRBS 11. Again, we wanted to make sure that we compare our results between PRBS 11 and PRBS 31 to make sure that our results are aligned. As we all will know, no one likes surprises. These two simulations with the two different PRBS patterns resulted in I's that are very similar in I dimensions and other specs. This gives us confidence that the correlation between simulation and measurement that we are seeing at PRBS 11 would also apply to PRBS 31. These simulations that you're looking at here on this slide were done at both BER of 10 to the minus 6 and also BER of 10 to the minus 12. The results seen are from BER of 10 to the minus 12, and also the I dimensions and I measurements at the tables at the lower half of the slide are reported at BER of 10 to the minus 12. In this slide, what we're looking at is an internal I capture that is built in within the DFE. And we want to see how this works. It's worth mentioning before we get in deeper that 16 gigatransfers per second translates to a UI of 62.5 picoseconds. So when you see on the horizontal axis the units are in UI, you can realize what those numbers would be in picoseconds. Keeping that in mind, let's take a look at how this I capture, internal I capture works. The DFE will calculate the I's width at the slicer's offset voltage. Here we have an offset voltage of about 37 millivolts. If we look at the internal I opening plot at 37 millivolts of offset, what we see is an opening that is 0.49 UI, and that is marked with a black arrow in the eye that you are seeing in front of you. Recalling that each UI is 62.5 picoseconds, we see that based on the internal eye measurement, we expect the eye width to be about 31 picoseconds. Now let's look at our simulation and measurement results and compare them. So we have them on the same slide, and we want to see what we get. As you can see in the table at the top right, there is very close correlation between simulation and measurement. For example, as we just discussed in the previous slide, we expect the eye opening to be about 31 picoseconds. Simulation results at BER of 10 to the minus 6 show an eye width of about 30 picoseconds. So that's a very good correlation. We can also see that eye heights of the simulations are also closely matching. What you can also see at the bottom right of the screen is the contours for the eye at both BER of 10 to the minus 6 and BER of 10 to the minus 12. This is important because we want to make sure that our model will perform at the PCI 4 specs BER required. As you can see from this graph, the eye is still wide open even at a BER of 10 to the minus 12. You can also see the timing bathtub at the left bottom, and you can see that the walls are nearly straight, which correlate back to the contour plot on the right bottom that we have looked at. Jim, if you want to talk about the setup.
Yes, this is the hardware setup we used for the silicon test measurements. In the middle, you can see the evaluation board and the PHY test chip in the middle of it. And the 16 gig TX transmitter of the test chip is connected across a legacy backplane connector or channel via two backplane paddle cards. The paddle cards there on the left and right. And through these two sets of paddle cards, you can transfer the signal from the transmitter out to the backplane and back into the receiver of the 16 gigabit test chip to allow for a full end-to-end full system simulation. Now, the PHY is capable of both generating and verifying multiple PRBS patterns, as well as capturing the receiver output eye, as you saw earlier in the presentation, using an internal embedded scope. The measurements from the internal eye capture were used for the correlation to the model simulation results that will be shared in the next few slides.
Okay.
Go ahead, Peg.
Okay, thank you. So that was a good segue into simulation versus measurement. We can create models and run simulations. If they don't correlate with the actual physical board, there's little value to them. So a very important part in completing the circle is comparing simulation results with actual bench measurements. And that is the next step that we have done. So in this slide, what you're seeing is our comparison of simulation and measurement results. As you can see, there's very close correlation between the simulated waveform and the measured waveform. So the waveform that you see at the top half of the screen, the left half of it is simulated and the right half is the scope result. And you can see again the eye dimensions are closely matching. For this comparison in this simulation, what we have done is we have used a preset of 0 with PRBS pattern of 11. In addition to the waveforms closely matching, as can be seen, we've also passed both the simulation and measurement waveforms results through the SIG test. For measurement, this is very straightforward. For simulation, what we did was we sampled the waveform at the rate specified by the SIG, and we saved this waveform in ADS. We then took this saved waveform and inputted this saved waveform into the SIG test and ran it to make sure that the simulation also passes the SIG test. You can see the SIG test results at the bottom of the screen, and both waveforms pass at no surprise since we can see the eye dimensions are very good. We repeated the same procedure for preset 7, still using PRBS 11. Again, as can be seen, there is very close correlation between simulation and measurement results, and both of our waveforms are still passing the SIG test. We only used presets 0 and preset 7 because of the amount of channel loss, and because these are the only two presets that would provide adequate equalization for our very lossy channel, which, as discussed earlier, is following the guidelines of PCIe 4. Recall that our composite channel has, at 60 gigatransfers per second, has about 33 dBs of loss. So after all of these tests, we can confidently conclude that our model performs very well, simulates rather quickly. All of these results were gathered in a few minutes, and simulation and measurement results correlate very well. Jim also showed in an earlier slide that the model behavior closely matches that of transistor-level silicon. So we believe we have created a high-fidelity model, and we have tested it in various ways. Now, we're going to do a quick recap of the topics that was discussed in today's webinar. We first showed that we can develop a high-fidelity IBIS-AMI model that can be used for quick and accurate link simulations. We use these IBIS-AMI models for our PCIe 4 transceivers because IBIS-AMI models are widely used by SerDes vendors and by system developers. After we also discussed how these IBIS-AMI models can be generated and how they can be validated. And finally, we showed very close correlation between our simulation and measurement at 16 gigatransfers per second for our PCIe 4 link. We also, in the validation of the model process, showed very close correlation between our simulation and our transistor level simulation. Now what we want to close with is reiterating that high-fidelity IBIS-AMI models can significantly speed the design cycle, and they can also assist the system designer in predicting the chip's behavior correctly and accurately, even in the early stages of the design, before the chip is out. Thank you very much for your participation. I'll pass it over to Bill.
Before we begin the question and answer session, we'd like you to first help us improve our webcast and answer a couple of short questions about what you saw today. In the slide window, please select the answer that you feel best. First, please rate your overall satisfaction with this webcast. Next, based on what you heard today, would any of the below solutions have value in your work? Next, if you do have any interest, what would your time frame be? Next, are you implementing 16 gigatransfers per second PCIe 4.0 in your current design? And finally, would you like more information about PCIe 4.0 PHY IP availability? Thank you for your responses, and don't forget our survey. So, first question is for Jim. How are you able to achieve this high level of PHY model accuracy?
Oh, thanks. Yeah, this is Jim. The high accuracy level is primarily, you have to put a lot of effort into the characterization of your channel. In this case, we call it a composite channel, but it's very important to model the channel as accurately as possible, just like modeling the IBIS-AMI model. You have to model the package, the connectors, any vias, any termination resistors. Everything has to be accurately modeled. Now, we use S-parameter models for the channel simulation, and we measure those. When I say model, they're measured very accurately. So the fidelity of the channel is just as important as the fidelity of your IBIS-AMI model. Thank you.
Okay. Peggy, is the IBIS-AMI model generated using an EDA tool?
Thank you, Bill. Yes, that is in fact the case. What we have used is we have used Keysight Technologies System View for generating IBIS-AMI models. System View is an EDA tool that assists model developers in creating their IBIS-AMI models in a systematic way. It has a rich component library that can be used for IBIS-AMI modeling. It also allows users to bring in their own algorithmic models if they have already developed those algorithms in other platforms. And it's important to mention that the models generated by System View are IBIS standard compliant and will simulate in other tools that are IBIS standard compliant.
All right. Jim, what advice do you have for AMI model users of your PHY to get close correlation in their designs? Oh, I think Jim lost his audio. We'll come back to that question. And I have another one here for Peg. Which Keysight scope was used for the measurements?
The scope that was used for these measurements is an Infinium V-series scope, and we use the 33 gigahertz scope, even though that might have been a little bit of an overkill for this. This particular scope is the industry's best in class for signal integrity, and because of its superior measurement accuracy. And it's worth mentioning that we use the real-time scope because real-time scopes are required by the spec.
Okay. I don't think Jim's quite back yet, so let's move on to another one for you, Peggy. How do you do specifications compliance?
That is an excellent question. There are, in fact, two distinct ways that this compliance can be done. You can run simulations. You can run a simulation-based compliance, I should say, using our compliance test benches in ADS. What this would do is this would help you design your system to spec and make sure that your system performs and passes the spec before necessarily doing board spins. Once your board is in, you can also do compliance testing in a measurement lab. And this would be done with scopes such as Keysight's Infinium, which is what we use. And the Infinium scope has a compliance app for PCIe, so you could use that and get the spec results and compliance reports.
All right. Here's another one you may be able to address. How did you get measurements from inside the chip to the scope?
That's also an excellent question. So the DFB in this case is designed to communicate and output results. So my understanding is this refers to the DFB internal eye that we showed. And that is actually reported back from the chip. And then what we actually did was we plotted that. So it's information that the chip itself outputted.
Okay. I'm not sure if this would be for Jim, but maybe you can answer this as well until he gets back on. we have somebody who's an RF engineer who's new to signal integrity. The simulation model shown on slide 20 is Ptolemy?
The model shown in slide 20 is Ptolemy. Let me quickly go back to slide 20 just to make sure we're talking same thing. No, actually. Thank you for the question. The screenshot in slide 20 is from Advanced Design Systems, or ADS. Ptolemy shares a GUI with ADS, so you might be seeing similar results, but this is actually using ADS channel simulator. And if you are interested about this, please do send us a note and we can work further with this and give you a more detailed answer after the webinar.
Okay. I think Jim's back here. So, Jim, is the 16 gig PCIe 4.0 PHY IP available at this time?
Oh, yes, it is. Synopsys, we've been demonstrating the 16 gig PCI PHY since about mid-2014. We've shown at many conferences, including PCI SIG and IDF in both the U.S. and abroad. We have also performed some 16 gig PHY interoperability testing with another vendor. So yes, it's available. Thank you.
Okay. Here's a question with regards to the slide that was talking about the 31 picosecond measurement. They wanted to know what was using the CHIPS I GUI software.
Yes, it was. That I is actually generated. There's an internal testing feature, a scope feature, and we internally, in parallel, can measure the I after the DFE, and that I is measured, via what we call an internal scope feature. That's part of the part of our PHY. It's not something that's unique to this testing, unique to our presentation. It's actually part of the PHY.
Okay. We just had a quick note. Somebody wants to know about the slides. There is a link button you can press to download a PDF version of the slides.
I believe the answer to that is yes. I heard in the instructions early on that the PDF would be available shortly after the presentation. You could also put an email in the comment box, and either I or Jim would be glad to send you a PDF copy of the slide.
Okay. Well, here we have another question. I'm not sure who this one would be for, but what is the minimum and optimum bandwidth required for measuring PCI Express 4.0?
Pega, I'm assuming they're asking. Oh, go ahead, Pega. I'm sorry.
Yeah, I was going to actually ask clarification. Are we talking about the optimum bandwidth for the S parameter measurement, or the optimum gigatransfers, basically frequency of operation, or the gigabits or gigatransfer point of the PHY? I'm not clear about that. Jim, if you're more clear, please go ahead and answer.
I think perhaps they're asking about the hardware. Are they asking about the hardware capabilities and the bandwidth limitations of the hardware? Okay.
Yes, I think that's the case. So, okay.
Okay, so if they're asking about the bandwidth of the hardware, I would say for the 16 gigatransfers that we had, we probably could have done with a scope with a lower speed. We went with a 33 gigahertz scope because that's what we had available. I would say about probably 20 gigahertz would have cut it.
Okay. Here's a question. How were the models verified, and were there behavioral models used?
The models were behavioral. So IBIS and IBIS-AMI by definition are behavioral models, and they were verified. Jim can more speak to the process while he was developing the models, and I can speak to the validation afterwards. But we did rigorous testing. We tested a lot of different conditions, and we compared with silicon, actual either silicon measurements or transistor level simulations. We have highlighted a few sets of results that we thought would clearly show correlation, but there was a lot more tests done in the background. Jim, if you want to add to that, please go ahead.
Yeah, the models themselves, they're algorithmic or behavioral in nature, but they're derived from circuit simulations, as I mentioned earlier. And though these models are behavioral only in the sense that they reflect the algorithmic function of the actual circuits, but any non-idealities, any limitations of the circuits are also modeled. So using a system view, the modeling tool, system view modeling tool, I recreate the model, and then I extract parameters and apply those parameters to the model. So what you have is, in a sense, behavioral, but I would call it more algorithmic and also more accurate than behavioral models because of all the parameters that are extracted from circuit simulations. And those model simulations are run to verify that these algorithmic models are actually responding just as if the circuit would respond.
I see. Why is PRBS11 used in measurements, and is PRBS11 required by the PCIe Gen 4 standard?
So we actually used PRBS11 in the lab because at the time that we ran these simulations, the PCI 4 pattern was not available. As I'm sure everyone knows, PCIe 4 is still a spec that's in development. So we used PRBS11, believing that it is the closest pattern that we could get to our PCIe 4 pattern, and that was the reason that we used it. And it also gave us fast simulation. We could run simulations, lab measurements rather fast.
Okay. How were the S parameters derived for the filter design?
So the only S parameters used for this demonstration were for the channel. Can you clarify what you mean by filter?
They weren't specific. We'll have to probably see about another question coming on for that, in which case why don't we move on to one of the next ones here. What about the power-aware IBIS-AMI models at 16 gigatransfers per second? Will power issues need to be simultaneously analyzed along with the channel itself?
In terms of PI analysis, if that's what's being asked, is another feature of the models is that it allows you to model jitter and apply a jitter to your models. Now, the way we model jitter is we effectively assume there's noise in the system. In the model itself, most of the noise is intrinsic, but there's also external noise in the chip, and that noise, the frequency content of that noise as well as the magnitude of that noise is understood, and the jitter associated with that noise is part of the jitter number. So, in a sense, the power influence on the IBIS-AMI model is modeled by the jitter that's applied to both the transmitter and the receiver.
I want to add a short comment, Bill, if I may. I want to add a short comment to this. As Jim mentioned, there's various ways of modeling this. If you have a power-aware IBIS model, ADS is capable of running that simulation. A lot of times, as Jim mentioned, what you end up getting is that you'd actually represent that as receiver noise, and ADS can also handle that and simulate that correctly.
All right. Is the software simulation for the component level or the PCIe board level? I'm not sure if there's really a distinction there.
Yeah, I guess maybe they're asking whether it's just one link or is this the complete board. That's my understanding of the question. And it depends on what you want to do. Most likely, if you want to do a complete board, you'd want to do some sort of either SIPI analysis or EM analysis, which Keysight Technologies has tools that have the capability to do that. You can then bring those results back into ADS schematic and complete your simulations. the focus of what we did today was one or a limited number of end-to-end links because we're focusing on, I guess, pre-silicon or simulations with S-parameter results. If you want to talk about bringing in the entire board and let's say do SI analysis or PI analysis, we have other very capable tools that we'd be glad to discuss with you if you'd please give us a comment in the notes section and we'll contact you back.
All right, that sounds good. Here's a straightforward one, I think. Why are width and width at BER different?
That is an excellent question. I'm glad someone brought this up. So when you're looking at the iProbe in ADS and you only ask for width and height, it will actually report the largest width and the highest height, I guess, of the eye, and not necessarily BER bound. When you say width at BER, it will actually report the width of the eye at the BER that you had requested the simulation to be run. So, and then I included those, I meant to mention this and I forgot, is because I want to show the contrast that I always recommend that you use width at BER and height at BER and not necessarily rely on width and height. Because the value that you would be interested in is width at BER and height at BER. I hope that answers the question.
I think it should. Here's another one. For the testing and simulations done using the stressed eye compliance, let's start from the beginning. Was the testing and simulation done using the stressed eye compliance stress parameters?
To my knowledge, we did not use the stressed eye. Jim, if you recall, let me know.
No, we did not. It was PRBS 11 patterns, and for the TX, there was a specific pattern used for our TX waveforms. I don't recall the exact pattern, so.
Yeah.
Okay. We have time for one more question here. PCIe Gen 4 specifies 28 dB loss per channel. Why did you happen to use 33 dB loss per channel?
Yeah, I discussed a little earlier. 33 dB is only a result of the extra test equipment we had to add to measure and demonstrate this PHY simulation and testing. The extra loss in the paddle boards I mentioned earlier, and also the interconnect, the coaxial cables that have to hook everything up, were extra loss. So yes, the 28 dB is the target, but we had to run with 33 because we had to accept the overhead of the test fixtures, which added about 5 dB of loss.
Excellent. Well, this has been a great Q&A, but unfortunately we're going to have to cut it short. For those questions we haven't been able to answer yet, we'll be responding via email. And this concludes today's presentation. On behalf of Electronic Design, I'd like to thank you for joining the webcast today. Thank you to Keysight Technologies and Synopsys for sponsoring this event. Have a productive remainder of the day.